All right, it's 10:30. Let's get started. So, as you know, it's supposed to start getting kind of messy tomorrow. If it does and class is canceled on Thursday, your exam will be next Thursday, not Tuesday. Unless you want me to post a recorded video and then I can do a review, fine, but I don't care. But if we do have class on Thursday, it'll still be on Tuesday. It has been written. There is one question on there that I don't think anyone got right one time I gave it, so we'll see if y'all get it right. I will be sure to mention it's over chapter 4. Yeah, it's over chapter 4. So I mention it every time I teach the class. No one just pays attention. So I'm not going to tell you what it is, but it's not in this section. So last time we talked about the three types of probability. So we had classical, empirical, and subjective. So know to which all of those apply. So classical probability, each outcome is equally likely. And the other two, you have to kind of conduct experiments for one of them. And then the other one is just an educated guess. So know which one is which. And so this section, we're going to talk about addition rules. So we talked about this last time, but a little bit at the end, whenever we did that example with blood types. So in the previous example, I asked you to find the probability of getting a sum of 5 or a 6. And you cannot ask getting a sum of 5 and 6 because it's not possible to get those two sums simultaneously. So when this happens, these events are called mutually exclusive. So we mentioned this last time. And what does mutually exclusive mean? So mutually exclusive means they cannot occur at the same time. So for instance, like it says getting a sum of 5 or a 6, you have 2 dice, you can't add up the numbers and get a 5 and add up the 2 numbers and get a 6 at the same time. So then like it says, I could ask you to find the probability of getting a sum greater than 9 and an even sum because these two events overlap. So what two numbers overlap? There. So getting a sum greater than 9 and an even sum. So the numbers greater than 9 are 10, 11, and 12. The even ones out of those are 10 and 12. So 10 and 12 overlap. Ten and 12 are in the sums greater than 9, and they are even. Okay. I was making sure everyone is still muted. Okay. So then how are we going to look at this? We'll look at an example of drawing cards. So everyone knows the standard deck of cards, right? Or somewhat. Okay. That's what we're going to talk about. So you have 13 cards. And you have 4 of each of them. So you have hearts, diamonds, spades, and the clovers. Okay, close enough. So I was like, I know it's something like that. So, and then you have ace all the way up to king. Oh, one thing that we will note is an ace is not a face card. I looked it up last semester to make sure. So it's not a face card. So a single card is drawn from an ordinary deck of cards. Determine if the following events are mutually exclusive. Drawing a king and drawing a heart. So the thing you need to figure out, can these two events occur at the same time? Yes, there's a king of hearts. So that implies, since there is a king of hearts, these two events are what? Yeah, not mutually exclusive. Because they can occur at the same time. So, everyone understand why that one is? Because you have a king of hearts. Where is it? Right here. So the next one says drawing a face card or a 6, or drawing a 6 and a face card. So can that happen at the same time? No, because a 6 is not a face card. So therefore, these two events are mutually exclusive. Because all the face cards are right over here. Jack, Queen, King, with all 4 suits, and the 6s are right here. Obviously, they don't overlap. So we talked about this rule last time. If two events A and B are mutually exclusive, then what happens to their probabilities? Anyone remember? So if these two are mutually exclusive, then the probability of A or B is equal to what? Everyone remember this little U thing? That's for or. And the cap one like this, it's for and. So the probability of A or B, if we have two mutually exclusive events, can be found this way. The probability of A plus the probability of B. Do you want me to draw out why that is? Okay. So I'll do it on the board. It can be explained with a pretty easy picture. Holy cow, 33 people online. Okay, so say you have this box here. There's your sample space S, and you have two events, A and B, and they don't occur at the same time since they're mutually exclusive. So we'll talk about later that probability can be determined by area. So then if I want the probability of A or B, all I do is add up the two areas. So then that means the probability of A or B is the probability of A plus the probability of B. That marker kind of sucks. Does that make sense to everyone? So what happens if they overlap? If they have an intersection? Yeah, they're not mutually exclusive, and it will change that formula. So, is that the next part? I can't remember. Okay. There. If two events A and B are not mutually exclusive, so this is on the next page. So say we have something like this. Can you see that? Okay, cool. So here's S, say here's A, and here's B. So since they're not mutually exclusive, they're going to have some overlap in between. So when I take the probability of A, I'm going to take all of this area and this oval right here, and that's going to be the probability of A. And then I'm going to add the probability of B, so it's going to be all of the area here. Then this one again. So I've double counted this middle area twice. So what do I need to do? Subtract off the probability of the intersection. That's the addition, the second addition rule. So there's a problem on your practice exam that I posted that says, determine if these two events are mutually exclusive and explain why. So what I want you to do on that question is see, is this condition satisfied or not? If it is, then they're mutually exclusive. If it's not, they're not mutually exclusive. Everyone okay with that idea? The simplest way to do it is with Venn diagrams. So now let's look at a couple of examples. So it says a single card is drawn from an ordinary deck of cards where the sample space was on the previous page. Find the probability of getting a queen of hearts. Yeah, 1 out of 52. There's only one queen of hearts in the total deck. So how will you find this? So the probability, queen of hearts, I'm just going to say QH, is equal to the number of queen of hearts divided by the total number of cards. And like you just said, there's only one queen of hearts in a standard deck, and there's 52 cards total. So the probability is a 1 out of 52. Everyone understand that? So the next one, it says, find the probability of getting a queen or a heart. So are these two events mutually exclusive? No, they're not. And we actually just found the probability of getting one in the first part. So then we use what rule? The first or the second addition rule? Close. Second, because they overlap. So the probability of queen or heart would be equal to the probability of queen plus the probability of a heart minus the intersection, the probability of a queen of hearts. So if I do that, what's the probability of getting a queen? How many queens are there in a standard deck? 4, one of each suit. So that's probability is 4 out of 52. How many hearts are there? 13, one of each card. And we just found the probability of the queen of hearts in the previous part was 1 out of 52. So if I do that, what do I get? Yeah, 16 out of 52. You want to reduce it, that is 4/13. Divide the numerator and the denominator by 4. I don't know why I put 54. 52. So what if it said find the probability of getting a queen or a jack? What rule would you use? Yeah, the first one. You can't get a queen and a jack at the same time. So you use the first one. So this next one is why I told you that an ace is not a face card. So it says find the probability of getting an ace or a face card. So like I said earlier, an ace is not a face card. The face cards are just the jack, queen, and king. So these two events are mutually exclusive. So we use the first rule. So the probability of ace, or I'll just say face, is equal to the probability of ace plus the probability of face. What is the probability of getting an ace? 4 out of 52, there's 4 aces. What's the probability of getting a face card? You have 3 different face cards. with 4 of each of them. So if you do that, you get the same thing you did in the previous part, 16 out of 52, which is again 4/13. Wonder if my handwriting sucks today. No idea. There. Everyone okay with that? What's up? 12 over 52. So we have face cards were, where's the last page? I'll just show you on this one. So the face cards you had are Jack, Queen, and King. So there's 3 of them. And you have 4 suits, so 3 times 4 is 12. That makes sense? Okay. So this next part says you also need to know how to work backwards. So for example, if A and B are not mutually exclusive, and I give you the probability of A or B, and then 2 of the other probabilities, you should be able to find the third. So using that rule, you know the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So all you need to do is plug in these numbers and solve for whichever one it's asking. So we have the probability of A or B is equal to 0.35. So this right here is 0.35. The probability of A is 0.42. And the probability of B is 0.55. So we just need to find this probability here. So let's just leave it as it is, the probability of A and B. So how would you find it? So the way I'll do it is, so this probability is negative, so add it to this side, and then you'd have 0.35 plus the probability of A and B is equal to, add these 2 together, and you get what? Yeah, 0.97. And then how do you isolate this one? You just subtract over the 0.35. That implies you that the probability of A and B is equal to what? Yeah. So if we do that, subtract it over at 0.62. Everyone follow up to there. I did not know that. That is genius. Ooh, did not know that. Yeah, I don't use Zoom very much. I bought it last semester so I could do office hours online. Oh, is everyone okay with all that? Cool. So if you got online yesterday, I'm sorry, I forgot. I was dropping my bumper off to get painted. I cracked it like 4 years ago and I got sick and tired of it. So I was like, I'll just get a new one. So this is the hardest section. Fair warning. So if it's hard, does that mean it'll be on the exam? Yes. So multiplication rules and conditional probability. So we use different multiplication rules to find the probability of 2 or more events that occur in a sequence, so one after another. So for example, if we roll a die and toss a coin, we can find the probability of getting a head in the 6. And why do you think that is? If I flip a coin, is it going to affect the probability of getting a certain number on a die? No. So these are what we call independent events. So you need to know this definition. Two events A and B are independent if the fact that A occurs does not affect the what of B occurring. Yeah, the probability. Yes. Most of the true and false is definitions. So if you've actually looked at either of the practice exams, it's similar to one of them. Not completely similar, but similar in some aspects. If you notice, I actually changed one of the questions on one of them because I was like, this doesn't make sense. I just used someone else's from last semester. So if events A and B are independent, then what do you think happens to the probability of the intersection? So if I have the probability of A and B, if these two events are independent, then if I want to find the probability of the intersection, it just factors into the probability of A times the probability of B. So that should make sense. Just like the previous example, we said if we toss a coin and we roll a die and we're looking at what's the probability of getting something on each of those, it's not going to be affected. So the probability of getting one is going to be, the probability of getting both of them will be the multiplication of the two. So let's look at some examples below. So a die is rolled and a coin is tossed. Find the probability of getting a head and a 6. So it's literally the thing we talked about above. So since these two events are independent, one of the happening does not affect the probability of the other. That means the probability of getting a head and rolling a 6 is equal to the probability of getting a head times the probability of getting a 6. What is the probability of getting a head on a fair coin? Yeah, a half. And what's the probability of getting a 6 on a fair die? Yeah, 1/6. If you multiply those, what do you get? 1/12. So if you drew a tree diagram and you actually went heads, tails, and then you listed all the possible combinations you could have of 1 or 6, you would notice that there is only 1 head and 6, and there's 12 total outcomes on the last tree diagram. You want me to draw out what that means? Cool. So a single card is drawn from an ordinary deck of cards and then replaced, and a second card is drawn. Find the probability of getting a jack and then a 4. So why do you think these two events are independent? Yeah, because if you replace it. So this is the key word. Then replaced. So if we take a card and then put it back in, the probability on the next one will not be affected. What happens if I keep it? The total number of cards will go down by what? 1. So then the probability of the second one is affected. So we'll talk about that in a second. So the probability of getting a jack and then a 4, since these two events are independent, is the same thing we did above. The probability of a jack and 4 is the probability of a jack times the probability of a 4. So how many jacks are there? We have 4 out of a total of 52 cards. And then how many 4s are there? Again, 4. So 4 out of 52. So if you do that, that is quite a large number in the denominator, and I'll tell you what it is. 16 divided by 2,704. So if you actually compute that probability, it's 0.006. So just like I said a second ago, from the previous example, what would happen if we didn't replace the card? So if we didn't replace the card, I'll just show you what it says. I don't want to write all that out. So if we didn't replace the card, then the probability of a 4 in the denominator would be 51 instead of 52, because in the second draw, you would only have 51 cards because you took one out. Everyone understand that? Okay. So then here's another definition you probably should know. When the outcome or occurrence of the first event affects the probability of occurrence of the second event in such a way that the probability is changed. So that just means the probability of one happening affects the other. Then we call these events dependent. So it's basically just the opposite of independent. Everyone okay with that? Okay. So then the next thing, the second multiplication rule. So if two events A and B are dependent, then the probability of A and B is equal to, what do you think? This one you probably won't guess. The probability of A times the probability of B given A. So given that A has already happened, what is the probability of B happening? So this part here is what is referred to as the conditional probability of B. So the conditional probability of an event B is the relationship to event A that the probability that event B occurs after A has already occurred. What's up? Yes. There you go. Sorry. So do you want me to kind of like represent what that means? Okay. So I'll draw a little thing up here on the board. So last semester when I did this, I just confused everyone. So hopefully it makes more sense. So we'll see how it goes. So say you have two things that happen. That'll work. C and A. So I just wrote it backwards anyway. We're always starting on a hot note. So given that A has happened, what is the probability of B happening? That's what it's saying. So given that this has already happened, what's the probability that this happens? So it should be the ratio of the probability of both of these happening divided by the probability that this already happened. So that's what it's saying. So using this idea here, what should be the conditional probability of B given A? So if I said it's the ratio of both of these happening divided by this, what is this probability here? The probability of A and B divided by the probability of what? A. So this is referred to as the conditional probability, like we just said. So what if B and A are independent? Then how would this affect the conditional probability? What do you think? So if B and A are independent, then this probability does what? Probability of A and B, if two events are independent, breaks up. The probability of A times the probability of B divided by the probability of A. What happens? Yeah, cancel the probability of A, and you're left with the probability of B. What does this say? The probability that B happens, given that A has already happened if two events are independent, is not affected. So it's just the probability of B. Everyone okay with that? So what if event B occurs first? That's just saying what happens if I switch A and B. What happens to the rule? Yeah, you divide by the probability of B. So it's saying if I do this instead of this. Yes. And so whenever your homework, it'll say, given that this has happened, what is the probability that this happens? So this is the given condition on the right, and this is the condition we want. So I'll look at an example in your homework to illustrate it. Oops, something dropped. So the next thing, where is it? There we are. Thanks. So where's that? There's 3-1. So this is a test for the independence of two events. So one test that helps to determine if two events A and B are independent is the following. So this is the rule. So two events A and B are independent if the probability of B given A is equal to the probability of B. So that's just what I did up here a second ago. So I'll erase that now since I changed the letters. So, or the probability of A and B factors into the probability of A times the probability of B. If either of these conditions is not satisfied, then the two events A and B are said to be dependent. So I think there's one question or two about this on your homework, and there's also one about the mutually exclusive ones. I'm not for sure about this one. I know there's one about two events being mutually exclusive. I saw it the other day when I was looking at it. So let's look at this example on the next page. I'm going to do it on the board. So where's the next one? A jar of marbles contains 6 red, 4 blue, 9 yellow, and 3 green. So what did it say? 6 red. What was the next? You said 3 green. Is that it? Cool. So obviously, first thing you should probably do is figure out how many total marbles there are. So 6 plus 4 plus 9 plus 3 is 22. So the first part, Find the probability of drawing a blue marble and then a green marble. So let me see, does it say? Okay, so in the top it says if we draw 2 marbles with replacement. So then what do you think the 2 events would be, independent or dependent? Independent, because you're putting that marble back, so the probability in the second draw will not be affected. So, and this can be broken up into the probability of blue times the probability of green. So the number of blue marbles is 4 out of 22. And green is 3 out of 22. So that gives you 12 out of 484. Did I do that right? Awesome. So 2 yellow marbles. So that's probability of yellow and yellow. So since we put the marble back after we draw it, that's just the probability of yellow times the probability of yellow. What's another way you could write that? Probability of yellow squared. You're multiplying the same thing twice. So with the probability of getting a yellow, there's 9 yellows out of 22 total. So it'd be 9 out of 22. And then you square that. So that's 81 out of 484. What's up?
Would we be able to answer in decimal form or does that?
Yeah, it doesn't matter. I'm pretty sure on the exam I put how many decimal places, or it says just leave it as a fraction. I'll have to check it. But I really don't care. I just like you to leave it as a fraction. That way I know that you got it exactly right, because sometimes you'll enter it in the calculator wrong. And that gives you the wrong answer. I'm like, where did that come from? So sorry, I'm stuffy. I can't stand those allergies. So the second one, or the second part, if 2 marbles are drawn without replacement, find the probability of doing this and this. So it's just the same thing. Golly. But instead, I am not replacing the marble. So then this, which one is which? Green, so blue and green. So this word right here would change to the probability of green given that a blue has been drawn. And the second one would be the probability of yellow given a yellow was drawn. So what do you think will change? So if I drew 1 marble and didn't put it back, how many marbles do I have left? 21. So since I drew a blue marble, that still means I have the total number of green marbles I started with. So that's 3 out of the new total 21. That gives me 12 out of 462. Is that right? Yes. Yeah, what's up?
Whenever it says without replacement, so how do you know it's only one thing?
Because we're only saying, so find the probability of getting a blue marble and then a green. So we're just trying to find the probability of getting that 1 blue marble. So if it says A, then that just means 1. Does that make sense? So find the probability of getting a yellow and then a yellow. So the first probability of getting a yellow will be what? Yeah, 9 over 22. What will be the second? Yeah, 8 over 21, because you drew a yellow and didn't put it back. So there's 8 remaining. Then you have 21 marbles. So that's 72 out of 462. Is everyone following how I did that? Okay. I'm gonna go blow my nose, and I'll be right back. Have I confused anyone yet? So this next thing here, you should know how to do. So it says use the table to find the following conditional probabilities. So I guess I'll just do it on the paper since it has all the numbers. So here. So the first thing you should do, if you're given a table like this and it doesn't give you the totals, you should do it. So this row total here, 36 plus 14 is 50. 22 plus 28 is 50. And please do not do this. I had someone do it last semester. What is 50 plus 50? 100. What is 14 plus 28? 42. What is 36 plus 22? 58. Please don't give me a total of 200. That happened multiple times. Yeah, every semester someone will do it. And I always say don't, and they always do. So they add this total together with that total. If you literally just add all the numbers in here, you get 100. Just do it that way. It's easier. That way you don't mess up. So if one person is selected at random, find the probability that the person is female given they don't smoke. So know how to read this. The probability of female given they don't smoke. So this given condition is the one on the right. So I'm going to write it as this: the probability of female given non-smoker. So by definition, it is equal to the probability of female and non-smoker divided by probability of non-smoker. So how would I find this one in the numerator, the probability of female and non-smoker? You just looked at how many female non-smokers are there. So female and non-smoker, there's 28 out of the 100 total. So that probability will be 28 out of 100. And what's the probability that they're not a smoker? So we have 42 non-smokers out of the 100 total. So these hundreds will cancel out. That leaves you with 28 out of 42. You want to reduce that, that's 2/3. Everyone understand that? So Find the probability the person is a smoker given they are male. So probability of smoker given male is equal to what? Yeah. Yep. Probability of smoker and a male divided by the probability of a male. So how many male smokers do we have? You have 36 out of the 100 total. How many males do you have? 58 out of the 100 total. Oh, no, 50, my bad. I did that column. 50 divided by the 100 total. Again, the hundreds cancel out. That leaves you with 36 over 50, which is 0.72. If you want to, you don't have to. So the final one, the person is not a smoker given that they are male. So that would probably be the probability of non-smoker and male divided by the probability of male. So how many non-smoking males are there? 14. And how many males are there? We just said again 50. So again, the hundreds cancel out. It leaves you with 14 over 50. If you're going to reduce that, that's 7 over 25. Okay, so the next example, know how to do. I'm pretty sure it's on your practice exam, or something like it. So, of PhD students, 52 have paid assistantships. In other words, if a PhD student is selected randomly, the probability they have an assistantship is 52% or 50.52. If 3 students are selected at random, find the probability that. So, selected at random. What does that imply about these 3 events in a row? Yeah, they're independent. So independent. So if I want the probability of 3 paid assistantships, so I just put PA, how would I find that? You take the probability of the first getting a paid assistantship times the probability that the second gets a paid assistantship times the probability that the third gets a paid assistantship. Another way you could write that is the probability of paid assistantship what? Cubed. So, and the probability of a paid assistantship was 0.52. So it would just be 0.52 cubed. And what does that give you? Yeah, 0.141. So the next one says, find the probability that none have assistantships. So it's just the probability of 0 paid assistantships out of 3. So that would be equal to the probability of no assistantship times the probability of no assistantship times the probability of no assistantship. You can again write that as the probability of no assistantship cubed. What is the probability that they don't have an assistantship? Yeah, 0.48. So the probability of not having an assistantship is just the complement of having one. So you can find the probability of not having one by 1 minus 0.52, which is also 0.48. And then you cube that. What does that give you? Yep. 0.111. So, do you notice a relationship between part B and part C? Anyone got a guess? So C is the complement of B. So if you get at least one right, that's the opposite of getting none right. Think of it like that. Does that make sense? So the probability of at least one assistantship is the complement of this one. So I can find this by taking 1 minus this. Does that make sense? It does not? Okay, so think of it this way. You get, how many slots are there? 3. So, oh, I probably need to put this over here so they can see. So, say you have 3 slots that we're talking about here. So say we have 0 paid assistantships. So that is no assistantship, no assistantship, no assistantship. So the complement of this is that if at least one has it. So that would be the probability of a paid assistantship, then no assistantship, no assistantship. Or you could do it this way. Oh, there's too many ways to do it. No assistantship. Assistantship. Is that right? Yes. And then okay, what's the last one? That one and that one. And then the last one is so this first one here, all 3 don't have an assistantship. So think of it this way. If all 3 don't have an assistantship, the complement of that is at least one of them does. So at least one of these people has one. Does that kind of make sense? So why do I say use the complement? Because the probability that at least one of them has it is the probability of all of these added together. Do you want to find the probability of all of those? No. So that's why we use the complement. Because you can find the probability of all these by taking the probability of this and subtracting it from 1. So then using that idea, what is the answer to part C? Yeah, 0.889. The probability of at least one is equal to, remember it this way, 1 minus the probability of none. So in that case, it would be 1 minus 0.111, which is 0.889. So, and then at the bottom, I put remember. Oh, you can't see it yet. Let me flip around again. So remember, for at least ones, get the complement. So find the probability of none, then take 1 minus it. It's going to be a lot easier. So I gave one of these questions on the first exam last semester. How many people do you think did it right? More than got the other question right. I can't remember. It was probably like 50%. Most of them gave me the wrong thing. So just know for at least one, use 1 minus the probability of it not happening. So it'll use that idea on your homework problems too. What's up? 2. So then you could do it. So look at the number of ways you could get 2 assistantships. So you'd have to just basically list them out. So you'd have to add the probability of this one, probability of this one, and the probability of this one. And just add those up. Does that make sense? The formula, so that would be, what is it, 3 ways? I'm trying to think of it to choose one or not. 2, 3, choose 2. Yeah, so it would be choose K. Yeah, it's a binomial one, I think. This way, so N, choose. Three, choose 2. The probability of getting assistantship to the second power times 1 minus the probability of not getting it. This is something we do in the next chapter. To the that. So think of it this way. This is what is called a combination. So we're looking at the 3 spots and we're choosing 2 of them to get paid assistantships. Then if 2 of them have a paid assistantship, that probability will be represented by 0.52 squared. And then the probability that they don't have one will be 1 minus 0.52. So that would be the 0.48 to the 3 minus, that should be 2, not 1. The 3 minus 2. So this just simplifies to 3 times this. So that's 3 of these, and the probability of each of them is the same. Does that make sense? This is what is called the binomial formula. Oh, crud. You don't need to worry about that yet, Avery. It's in the next chapter. I can show you what I was saying. Here. So she was asking what happens if we ask for 2 paid assistantships. So you can find it using this formula here. So for each 3 slots, you choose 2 to have paid assistantships. So that's 3, choose 2. And then you have the probability of them having a paid assistantship squared because it's for 2 people. And you have the probability that they don't have an assistantship to the 3 minus 2. So
we don't add all 3 paid assistants to the probability?
no, like she just said 2. If she said at least 2, then yes.
Okay.
If she said at least 2, then you'd add this one as well. Does that make sense? Okay. So then the last thing we'll talk about in this chapter is what is known as counting rules. So this got a little bit easier since when I first started teaching it, we took something out of it. So the first thing we'll talk about is what is called factorial notation. So has anyone ever heard of factorials? Okay, so for any counting number n, that just means for any number like 0, 1, 2, 3, 4, 5, we denote n factorial as n times n minus 1. Okay, good, I had it on there, times n minus 2 times all the way down to 2 times 1. So this one is quite weird. Note 0 factorial is equal to what? Yeah, 1. Sounds strange. So using this factorial notation idea, how many ways can 4 friends sit down at a concert? Just 4 factorial. So I would take 4 times 3 times 2 times 1, and that gives me what? 24. So we used to discuss permutations in this section, but we deleted them, so you're not going to worry about those. So then we'll go into combinations next because it uses this idea of factorial notation. So the combination rule as given by your textbook. So the number of combinations of R objects selected from N objects, which is denoted NCR, is given by the formula here. So NCR is equal to N factorial divided by N minus R factorial times R factorial. So another way you write it is this, like that. So I guess I'll show the people online too. So another way to write that NCR thing it says is this. N choose R. So that is equal to N factorial divided by N minus R factorial times R factorial. So do you want to use that formula? The answer is no. So what do you think the easiest way to do it is? Yeah, obviously your calculator. So then I'll show you how to do that for this first example. And then I'll show you how to use the formula as well on the second one. There it is. Everyone ready? So if you have a TI 83, then what you want to do first is enter the number for N. Then go to math probability. Then choose NCR. And then you'd enter the number for R. So I guess you could do it the same way on an 84. It just does the same thing. It just gives you spots to put them. But on the 83, it won't give you spots. It just says like 5 NCR 2. Then you'd enter it after that. And then when you hit enter, it tells you what it is. What's up? Yeah. So, oh, whoops, wrong button. So go to math probability NCR. Then if you have an 84, you can just enter in the N on the left-hand side. So it'd be 5. Then enter the R on the right-hand side. It would be 2. And then just click out to the right of that and then hit enter. Figured out? Cool. So if you do that, you get 10. So now let's look at the second thing below. So use the formula above to find the number of combinations of 5 objects selected from 10. So I'm saying actually use the formula to do it. So I'll show you how to do it or simplify it. So in this case, N is what? N is 10, R is 5. So then enter those in here. So we have 10 choose 5 is equal to 10 factorial divided by 10 minus 5 factorial times 5 factorial. If you do that, this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Another way you could say is just 5 factorial. So then the denominator, 10 minus 5 is 5. So you have 5 factorial again, and then 5 factorial again. One of the 5 factorials cancels out, and it leaves you with 10 times 9 times 8 times 7 times 6 divided by 5 times 4 times 3 times 2 times 1. That's how you'd simplify it. So if you do that, I have no idea what that is in the numerator. 30,240. And at the denominator, 5 factorial is 120. Yeah, 120. If you simplify that, it gives you 252. So do you want to use the formula or use your calculator? Yeah. So let's check and see if we got it right. I didn't really check to be sure. So I'm assuming it's right. So 10, choose, oopsies, wrong button. 5, ta-da, I'm still a genius. Not really, what's up? Okay, so N is the number of total objects. So it'll always be the larger number. So you're taking R objects from N objects. Yeah. Because if you flip the two, you get a fraction. And that doesn't make sense. Can you show the calculator thing again? Yes, I can. So here, so you go math over to probability, down to NCR. And then on the left-hand side of the C, you'll enter in the number for N. So in our example we were doing was 10. And then the second one on the right will be the value of R. So you'd enter in 5. Then you go off it and hit enter, and it'll tell you what it is. Does that help? No problem. So let's look at a couple of these review questions real quick, I guess. So I will not make this review bonus because grading those was awful. I was sitting in one of my classes grading them. I was in combinatorics and he was explaining something and I was just sitting there typing. So a single card is drawn from an ordinary deck of cards. Find the following probabilities. So the first one, drawing a face card. 12 out of 52. There's 12 face cards out of 52 total. Drawing a spade or an even number. So you got to think, are these mutually exclusive or not? They're not. There is even number spades. So you'll have to take the probability of S or even is equal to the probability of getting a spade plus the probability of getting an even minus the intersection. So how many spades are there? So we got 13 spades out of 52 total. How many even cards are there? This one's weird. So easier way, look at one suit. 2, 4, 6, 8, 10. 1, 2, 3, 4, 5. And there's 4 suits. 5 times 4 is what? 20. 20 out of 52. Now, how many even number spades are there? So we're just looking at one suit, and how many even numbers were in each of those? 5. If you do that calculation, you get what? What'd they say? 28? Yep. 28 out of 52. Drawing a red card and an ace card. This is looking at the intersection. So it's looking at how many red aces are there. How many? 2. You have a diamond and a heart. So there's 2 out of 52 total. So this next part gets a little bit trickier. So we still have 3 minutes, so we can get through it. So now assume we draw 2 cards without replacement. Find the following probabilities. So drawing 2 red cards. So what's the probability of drawing a red card in the first one? 1/2, 26 out of 52. So if I don't replace it and I draw a red card, how many red cards are left over? And how many total cards are left over? Yep, 25 out of 51 is the second. Oh, crud, what is that? It is 25 over 102. Don't say something online. Okay. So the next part, drawing a 7 and then an even number. So what's the probability of getting a 7 on the first draw? 4 out of 52. What's the probability of getting an even number on the second? What? Yeah, it was. So how many even numbers are there if we just draw a 7? So we said there was 20 total, right? And we drew a 7, which isn't an even number. So we'd still have 20 out of 51. That simplifies to 20 out of 663. Could you go over D again? Yes, I can. So let's see, I'm going to make sure. So Kevin, I shall explain. So the second one here says, what's the probability of drawing 2 red cards in a row? So this first one here, the probability of getting a red card on the first draw. So there's 26 red cards total out of 52 total cards. So the probability of drawing a red card on the first is 26 out of 52. And then if I'm looking at the second draw here, I've already drawn 1 red card. So that means the total will go down by 1 for the number of red cards I can draw. But also, since I drew 1 card out of the deck, then I have 1 less than 52. So I have 51 remaining. So the probability of getting a red card in the second draw would be 25 out of 51. Does that make sense? You're welcome. All right. So if I don't see y'all on Thursday, have a good Thursday. If I do, see you then.